Hello everyone. So this is the first video lecture on the real analysis. We deal with the concept called countability and we will solve few problems in the next lecture. First we try to understand what is the theory in this countability part. First thing is we need to understand what is 1 1 and onto. So let me consider a function f from a to b. If there are, let me say, a, b, c, d, 4 elements are here and the 4 elements are here. If I can map, see, as the name suggests, 1 1, for one fellow there should be one friend. So let me say a is a friend of 1, B is friend of 3, C is friend of 2 and D is friend of 4. So here for every fellow in this first set there is a friend in the second set and it's 1 1, only one friend is there. So it's called 1 1 mapping. But this is not 1 1. This is not 1 1, this is many 1. Is it clear? So while defining the function, the first set, what else I written A, it is called domain of the function. The second set, what else it will be there once you define that function, it is called codomain. It's not necessary that every element of this codomain should be mapped. Few elements may be left and you can consider a portion of it for the construction of the function. In that case we say this is called a range of f. For example, here the range of f is 1, 2, 3, 4. Here the range is just, let me say, domain here is ABC. Codomain here is 1, 2, 3. What is the range? Range is the elements that are associated. 1 is in the range, 2 is in the range. Is it clear? So simple, you will get the simple problems. So we can understand those things in the most trivial way and we can solve few examples and we can come across, we look into some problems, we can easily solve them if we know some standard results. So now we are clear with the 1 1 property. Then what is onto? Onto in the sense, see, already we know what is domain and we know what is codomain. Always note that range is contained in codomain of f. Range, that is this range of f 1, 2 is contained in this set. If the range is equals to codomain, then we say that f is onto. Is it clear? The range should be equals to codomain of the function, then we say that the function is onto. So if the function is both 1 1 and onto, then we say that it is an bijection. And one observation is, the first observation what we want to make is, let me say I have A, E, I, O, U and here I have 1, 2, 3, 4, 5. I will map A to 3, E to 1, I to 2, O to 4 and U to 5. How many elements, whether it is 1 1 first of all? See, each element, 1 is mapped to only one element, single element is mapped to single, so it is 1 1. Whether it is onto, what is the codomain? Codomain is this set B and this is the set A. Codomain is B. What is the range? How many elements are associated? How many elements are mapped? See, here 1 is also under consideration, 2 is also under consideration, 3, 4, 5. So it is nothing but B. So domain and the range are equal. So it is onto. That means it's an bijection. If I define F, it's an bijection. This map F is a bijection. But this will make us to think about the first observation. How many elements are there in the set A? 1, 2, 3, 4, 5. How many elements are there in the set B? Here also I have 5 elements. So if there is 1, 1 and onto correspondence between any finite sets or else any sets, if there is an 1, 1 and onto correspondence from A to B, then the cardinality of A is cardinality of B. This is the first observation. Is it clear? So if you have the first set and the second set, if we are success in finding 1, 1 and onto map, then it's clear that the number of elements in A and B will be same. Is it clear? Next is, what is equivalent? So we say that two sets are A is equivalent to B, two sets are equivalent if there is 1, 1 and onto correspondence. Or else 1, 1 and onto property must be there between A and B, then we say that A and B are equivalent. Is it clear? This symbol stands for equivalent. Now, what is countable set? See, you should be clear with this. What is the definition of countable? A set A is said to be countable if it is finite. If it is finite or it is denumerable. So you are familiar with the finite set, the set of all vowels, the set of alphabets in the English. So these and all are finite sets. But denumerable is what? Don't be panicked. Denumerable, it says you take any set. If it is, let me say, S is the set under consideration. If it is equivalent to set of all natural numbers, then we say that it is denumerable. Any set, if it is equivalent to natural number, we say that it is denumerable. Finite in the sense, for example, A, E, I, O, U is there. How many elements are here? 5 elements. So A is equivalent to a set containing 5 elements. We write it as J5. Or else just say a set with 5 elements. Or else set of all English alphabets. Let me say B is A, B, etc. up to Z. Then B is equivalent to Z26. Is it clear? So we say that a set is countable if it is finite or it is denumerable. Now, what is uncountable then? Uncountable means it should not be countable. So negation of countable. Negation of countable means you should negate this. It cannot be finite, it should be infinite. R becomes and. Infinite and. Denumerable means S is equivalent to N. So S is not equivalent to N. If the set is infinite, so I negated this. R was there, instead of R I took and. S is equivalent to N, I took S is not equivalent to N. Is it clear? If the set is infinite as well as it is not equivalent to N, then we say that it is uncountable. Now, we start with the remarks. The first remark is, if it is denumerable, if a set is denumerable, it implies us that it is countable. It means if it is denumerable means it will come into this, so it will imply me it's countable. If it is equivalent to n, I can say that it is countable. Or else if it is finite, still I can say it is countable. But how about the converse? Is countable implies denumerable? No. Need not be. Why? For example, let me take this set itself. Whether this set is countable? Yes, because it's finite, so it is countable. If it is countable, whether it is denumerable, that is whether it is equivalent to n? No, it is not equivalent to n, it is equivalent to j5. So denumerable implies countability, whereas countability does not implies denumerability. Is it clear? Then we move on to second remark, which says if C is countable, if the larger set is countable, then the subset is also countable. That is, every subset of a countable set is countable. Is it clear? Third remark is finite union of finite set is finite. If you take finite union of finite sets, definitely it will be finite, undoubtedly. Then finite union of denumerable set is denumerable. Finite union of denumerable set is, in fact, countable union of countable set is countable. So this and all are the standard results which we are going to use. No need to construct the proof, just try to remember what all the facts are there. Then if A and B are countable, then A cross B is also countable. Set of all real numbers is uncountable. Set of all real numbers is uncountable. Then the set of irrationals are uncountable. But the set of all rationals is countable. In fact, Z is countable because Z is equivalent to n. Rationals is countable means Q is equivalent to n. That's what I had written. Is it clear? Then the next remark is, if I have the interval a comma b where the end points, the set of all irrationals, the set of all rationals in AB is countable. If you take this open interval AB, and if you think about how many rationals are there, it is equivalent to n. Is it clear? Similarly, the set of all irrationals, in this open interval is uncountable. The set of all rationals will be countable, the set of irrationals will be uncountable. Keep these things in mind. And what is an algebraic number? Any complex number, a complex number is said to be algebraic if it is a root of a polynomial with rational coefficients. then we say that that number is algebraic number. Why algebraic number? Because algebraic number has a nice property. Take down as a next remark. Algebraic numbers are countable. Algebraic numbers are countable. They will ask the question in the straight way itself. You can answer that. Then take any two interval in the real. They are equivalent. That means the number of elements in this interval is equals to number of elements in this interval, where A is less than B and C is less than D. If I take any interval AB as well as CD, or else take 1, 2 as well as 3, 4. The number of elements here is same as number of elements here. Or else take 5, 8. The number of elements here is exactly same as number of elements in this. Is it clear? Then next remark is all type of intervals in that we need to exclude some fellows. Those are empty set and singleton. Excluding this, excluding singleton and empty set are equivalent. In the sense, if I have 1, 2 which is closed at 1 and open at 2, whether it is equivalent to 3, 4, yes, it is equivalent, because all type of intervals excluding empty set and singletons are equivalent. Then the collection of all intervals with rational endpoints is countable. The collection of all intervals with rational endpoints is countable. Similarly, the next remark is the collection of all intervals with irrational endpoints is uncountable. Is it clear? Then we move on to characterization of infinite set. How does an infinite set will look like? Once we study these things, it will take half an hour to 1 hour if you just go through this. Then we can move on to what is the characterization of infinite set. See, characterization of infinite set is a set is infinite if and only if it is equivalent to proper subset of itself. First of all, we know what is this equivalent and we know what is this infinite. We need to know what is this proper subset. See, if let me say this is set A, the subsets will be, empty set will be always a subset of this, A will be always a subset of this. These are called improper subsets. If I have any set which is a subset of this, for example singleton 1 is a subset of A, this is proper. Or else 1, 2, this is a subset of A, this is proper. Is it clear? So here what else is saying? A set is infinite if and only if it is equivalent to proper subset of itself. See, for example, you can say if you have a infinite set, let me say A is an infinite set, and here also you consider a subset of it. Let me say this is A and this is a subset. B is a subset of A. If A is infinite, then this A is equivalent to the proper subset. B is a proper subset of A, So A can be made equivalent to this. Then we say that it's an infinite set. And this will work for infinite set. See, natural numbers is there. It is 1, 2, 3, etc. But it is equivalent to 2z. That is set of all even numbers. In fact, set of all even numbers is a subset of this. But we can show this natural number and 2z are equivalent. In the sense, if you have an infinite set, it is equivalent to proper subset of itself. 2z, that is set of all even numbers. Let me say 2n, because minus 1 will be there. 2n. Set of all even natural numbers is a subset of, proper subset of n. Is a proper subset of n. But you can say there is an 1, 1 and on to correspondence between n and 2n. You can always establish a mapping. So in that sense, if you have an infinite set, it is equivalent to proper subset of itself. So once we discuss few problems, everything will be clear. In the initial stages, try to understand what exactly that it says. Now, how does the cardinality will be? How does the chain of the cardinality? If I have one element, we say that singleton element is there. Then we say that if A is there, its cardinality is 1. If two elements are there, its cardinality is 2. Likewise, if there are in natural numbers, how many elements will be there? Or else in integers, how many elements will be there? As we know, n is equivalent to z. That means number of cardinality in n equals to number of cardinality in z. And we denote this cardinality equals to Aleph naught. Equals to Aleph naught. This symbol is like Aleph naught. So cardinality of n and cardinality of z, cardinality of q, it is Aleph naught. Then what is the cardinality of real? What is the cardinality of irrationals? Cardinality of real, cardinality of irrationals, cardinality of any interval. These cardinality will be, these are uncountable and these are countable sets. For countability, we say if it is equivalent to n, we say that its cardinality is n. If it is not equivalent to n, we say that its cardinality is continuum. So cardinality of R is continuum, or else cardinality of closed interval, or else any interval. You can say cardinality of this, it is equals to continuum. Is it clear? Then we move on to some arithmetic of cardinality. That means how to add. See, one thing you need to know here. So if S is any set in our hand, then it may be finite. Finite means, let me say k elements are there, where k is finite. K is less than infinity means it is finite. If you have two elements, k will be 2. If you have three elements, k will be 3. And if you have equivalent to n, then we say that it is Aleph naught. Cardinality of S is Aleph naught. If S is equivalent to n. And it is equals to continuum if S is equivalent to R. Is it clear? So arithmetic of cardinality is easy to understand. Kindly think in this way. N plus n is n. So Aleph naught is the largest fellow here. Whenever largest fellow is there, you consider the largest. If I add, don't write it as 2 Aleph naught. It is still n naught. Then n naught plus n naught. How many times? You say Aleph naught times, that is infinite times. Still it is Aleph naught. Because everywhere Aleph naught is there, the largest is Aleph naught itself. Fourth is n cross Aleph naught is Aleph naught. Fifth one is n plus c is, see here largest is continuum, because the cardinality is first is finite, then Aleph naught, then continuum. So finite will be there, which is less than Aleph naught. It is strictly less than. See, this is the chain. This should be the, if you have an infinite set, it must be equivalent to this, or else it must be equivalent to this. If you have an infinite set, either it must be equivalent to this or else equivalent to this. If it is not equivalent to this, if you have an infinite set which is not equivalent to this, then it must be equivalent to this. Is it clear? Then what is continuum plus continuum is continuum. Aleph naught plus continuum is continuum. Continuum plus continuum, continuum up to, let me say, n times is still an continuum. Then continuum plus continuum, how many times is Aleph naught times? Still it is continuum, because you can write it as Aleph naught into C, but in this largest is C, so you will say it is continuum. Then this is interesting. C naught to the power n, it is C naught. Aleph naught to the power n, it is Aleph naught. But this is important, 12th and 13th. 2 to the power Aleph naught is C naught, that is continuum. 2 to the power Aleph naught is continuum. Not only 2, you consider 3 to the power n naught, 4 to the power n naught, or else some k to the power Aleph naught, it is still continuum. Next is, what is 2, 3, 4, etc. up to k, up to continuum? It is 2 to the power C. So how is the chain of the cardinality? Chain of cardinality is this. This is singleton. This is a set containing 2 elements. This is the set containing 3 elements. So this is the set containing infinite, means the first infinite set will be Aleph naught. The second will be continuum. And next will be 2 to the power continuum. This is the chain of cardinality. Kindly study up to this. Then if we solve some problems, you can easily get through these things. This much is enough to understand what exactly countability is. Thank you for watching. We will upload the next video with the assignment questions and we will solve them so that we will get the clarity of what else the things that we studied. But one request from my end is, kindly read those things. If you have any doubts, let me know so that I can clear you in the better way. Thank you.